Hi everyone, my name is John Park. I'm a PhD student under the supervision of Professor Robert Heath. In today's talk, we are going to talk about the threshold-based antenna selection algorithm for dense cloud radio access network. Actually, Cloud RAN is the network architecture featured by a separated deployment of a base station, a base band unit, and the RF unit. And actually, there are several issues in the Cloud RAN, including the BBU processing unit allocations, or frontal minimization, or antenna coordinations. And today, we will focus on the antenna selection problem in Cloud RAN. In antenna selection problem in Cloud RAN, we want to select the antenna out of many antennas deployed in the field. And actually, the basic process is that the selection switch, which is placed in the middle between the BBU and the RF units, chooses a subset of antennas and make a connection with the chosen antenna subset and the BBU cloud. And actually, there can be several targets for antenna selection problem. And among them, we are focused on the low complexity. So we will investigate the low complexity antenna selections. Here's our setting. We assume that the uplink Cloud RAN, and so a user transmits a symbol through the network. And we also assume that one BBU is dedicated for decoding one user symbol. So, and the BBU can flexibly connect a subset of antennas. So this selection switch, as I mentioned before, the selection switch, when choose a subset of antenna, it make a connection to a BBU, which is dedicated for decoding user one symbol. And when the connection is completed, the symbol decoding is started. So now I'll explain some simple proposed algorithm. The proposed algorithm consists of two phases. At the first phase, which is called the distributed selection phase, each antenna determines itself to be included or not into a candidate set. And then at the second phase, called the random selection phase, the antenna selection switch randomly selects one antenna within the refined candidate sets. Therefore, we have two separated phases in the algorithm. And then we have to note that the required complexity in the algorithm is just a constant, because there is no centralized processing here. Because in the distributed selection phase, each antenna measures their distance or path loss from the user, and each antenna determined in the distributed way to be included or not in the candidate sets. And in the second phase, it's just all we have to do is just random selections. Therefore, we preserve the constant complexity. Clearly, there's a fundamental trade-off in the proposed algorithm. If we have too small threshold, like in this case, it is likely that no antenna is selected. It is obvious. And on the contrary to that, if we have too large threshold, the probability that too far antenna from the user is selected increases. It means that there is an optimal selection threshold for the proposed algorithm, which well balance these two extreme cases. To obtain such optimal selection threshold, we start model our network by using tools from stochastic geometry. So each antenna and the user is distributed as a homogeneous Poisson point process. And here we consider, and the Rayleigh fading is assumed, and as a decoding algorithm, we treat the other user's interference as noise. And here we consider two cases of outage, each of which is called the empty outage and the low outage case. Empty outage case means that no antenna is selected in the distributed selection phase, so it's likely to occur when we have too small selection threshold. And the second case, which is called the low outage case, is just a conventional outage event, which occurs when the SIR is lower than our target threshold. By using the tools from the stochastic geometry, we drive the closed form SI expression as a function of key system parameters. For example, the selection threshold and the antenna density and the path loss exponent and the interfering user density and the target SIR threshold. Here, the key idea for characterization is that we one of the key things of PPP's property is that when we condition on the number of points, that the points inside a limited region is distributed as a uniform distribution in PPP. So this is the key thing for to keep step for characterizing the closed form expression. Here we provide the validations, and we observe that our analysis is quite exact with the simulation result. One interesting point is that in the graph is that depending on the SIR, the dominant outage events is different. For example, at the low SIR region, the large threshold is more beneficial, as you see this. This is because the outage event at the low SIR region is actually dominated by the empty outage event. On the contrary to this, at the high SIR threshold, the small selection threshold is more beneficial, as you see in this regime. And this is because the outage event is dominated by a low outage event in this case. So now we start to optimize the selection threshold. The analytical challenge is that actually the derivative form does not have the closed form solutions. So we rather approximate to obtain the SIL distribution, and we rather tackle to optimize the approximate form of the SIL expressions. By using the approximations, the approximate optimal selection threshold is derived. And one point here is that actually it is inversely proportional to antenna density and the user density and the SIR target threshold, actually. The interpretation from this observation is that when there are many antennae in the field, only small selection threshold is enough to prevent the empty outage event. And second, also there are many interfering users. Actually, choosing far antenna becomes more fatal to the performance of the typical users. And finally, when the target threshold becomes large, actually the low outage event becomes more dominant. And for these three regions, the optimal threshold would increase when these values decrease. Now we provide another validation for our approximate optimal selection threshold. And in this graph, we observe that the approximate optimal threshold performed quite well compared to the another threshold, which is obtained by numerically. Actually, the obtained selection threshold can be modified for a case that there is a long-term shadowing, actually. Actually, the detailed proof is in the extended version, but the intuition is that to include the same average number of antenna in the candidate set with the case of there is no shadowing case. Therefore, by this intuition, when the shadowing factor degrades the signal power, the threshold should be increased to compensate it, as you see in this case. Here's our conclusions. We proposed the antenna selection algorithm for uplinking cloud RAN, which consists of the two phases. Using the statistics of antenna distribution, which is the fact that the antenna is distributed as a homogeneous Poisson point process, the SL coverage performance can be guaranteed with a low complexity compared to the other algorithm. And this ends my talk. Thank you very much. This is end of my first presentations.